Hello everyone. So today we're going to look at a version of energy called potential energy. So potential energy is energy that you can store in another format and then it can be converted to some other format when you need it. So how can we conserve energy or store it? Now, one way is by using chemical bonding. So for example, the energy stored in a battery is actually chemical energy. So the battery has different types of metals inside and some acidic solutions, and those reaction creates electricity when you have the right condition. But another way of storing chemical energy is probably less familiar with a lot of people, which is food. When you eat, you gain energy. But the energy in your food is actually also chemical energy. So when you eat the food and your body digests it, by breaking those chemical bonds, you get energy from the food released to your body. And that's how the energy from the food goes into your body. So the energy stored in food is stored as a chemical energy. And when you eat it, you're breaking down those chemical bonds from the food, you're digesting it, and that gives you the energy and the nutrients that you need. Now, we already talked about elastic force in the last chapter. So you can also use a spring or a elastic band to transfer energy to an object. For example, you can make some kind of for example, use the elastic band to make some kind of slingshot and you can shoot an object out. So obviously, while the object is all the spring is being compressed, there's some energy stored in it and you can release it if you let go. So elastic stored energy, for example, bungee cord, or a bow and arrow, or like a spring, etc., right? Now, the third one, electrical potential energy or electrical energy, which is the energy stored in static charge, so positive or negative charge. Okay, so if you have a lot of electron or a lot of proton coming together, and they would like to repel each other. So before you let go, they're being forced into place. And if you let them go, the electron is going to go around in the circuit. So that is electrical energy stored in static charge. So these are chemical potential energy, elastic potential energy, electrical potential energy. But what we're going to focus today is on the energy stored not in a battery, not in food, not in the elastic band, not in plus or minus charges, but the energy stored in our gravitational field, the energy stored in gravity. So, and that is called gravitational potential energy. Okay? So, gravitational potential energy. Now, this energy is based on an object's position. So it's based on an object's position. How far away is the object from the surface of the planet? Now, because you can't really go into the planet, right? So I guess the surface, which is ground for us, would be the lowest point. And then the further away you are from the ground, the more energy you have stored in the object. So when you let go, the more damage it will do to the target that it hit. Okay, so remember, energy, like money, you cannot really destroy it. You can use the energy and exchange it to other type of energy. So energy can be converted into different form. So for example, what is a light bulb? A light bulb is an object that converts electrical energy into light energy. And for example, a water electric kettle is a water boiler, which is converting electrical energy into heat, right? Into heat energy. So energy can be converted into different form. And when you do that, transferring energy from one type to another, and that's called work done, right? Okay, so now the equation for potential energy should be on your formula sheet. So I'm going to write it down right here very quickly. So gravitational potential energy. Now, since we do have different type of energy, we are going to start writing subscript again, just like how we write forces with friction FF, normal force Fn, and so on. So potential energy is based on the height of an object and how heavy the object is and what planets are you nearby. So those three things: mass, gravitational field, and height, mgh. This, if you recall, is exactly the same equation that we developed yesterday, which is the amount of energy you need to lift something off the ground, mgh, right? The work done that you need to transfer energy to an object by lifting it off the ground. Now, of course, energy is measured in joules, where mass is measured in kilogram. So mass is always measured in kilogram, and g is, well, acceleration due to gravity, and that's measured in meter per second square, and h is height, which is measured in meter. So these are: mass is in kilogram, acceleration is in meter per second square, and height is measured in meter. Okay, so now gravitational potential energy. So we have an equation that's based on the amount of potential energy on an object, and it's separate. It's based on three things, right? The planet, the mass of the object itself, and the height. So now when you think about it, so these are different scenarios. So let's say you have the ground right here, and so let's say you have a small object versus a giant object, but they are both at exactly the same height off the ground. So when they fall, they should be falling to the ground by the same speed if there's no air resistance, right? But because one object is less massive than the other one, so which one has higher potential energy? So even though they both have the same height off the ground, and even though they are both subjected to the same gravity because they are in the same planet, but the one that's more massive is going to have more or higher kinetic energy value than the one that is smaller, okay? Because it's mgh. So the more massive an object is, the more potential energy it has. Now remember, more energy means what? That means if you let go of the object, it will do more damage, transfer more energy to the ground and do more damage to it. Same idea. So let's say you have two objects with exactly the same mass, but one is higher and the other one is at a lower height. So one is here and the other one is higher off the ground. Then in this case, even though they have exactly the same mass and they are exactly on the same planet, but still the object which is higher off the ground is going to have higher potential energy from our gravitational force. Why would we say that this is the energy stored in gravity? Because, you know, the higher it is, the more time you get to accelerate, and the faster you hit the ground with, and the more energy and more damage you can do, so more work can be done to the ground, right? So same thing. So I guess the third one or the final one would be, so let's say, what if the two objects have exactly the same height, exactly the same mass, okay? So exactly the same height. Then you might say, Mr. Chang, then there is no difference, right? Well, but what if this one is on Earth and the other one is on the moon? So what is the difference between Earth and the moon? The little g value. Earth, gravitational force is 9.8. The moon, gravitational force is about 1.6-ish meter per second square, of course. So even though both objects start off the same height and same distance from the ground, same mass, but the force or potential energy on the Earth object is still going to be greater than that on the moon. Okay, so the higher it is, the bigger the planet is, and the heavier the object originally is, the more potential energy you can store in gravity with that object. And when you let go, the more damage it will do to the ground. Now, we keep saying the ground for every single one of these questions. Now, do we have to use the ground though? Well, the answer is no, because, I mean, what is ground? I mean, your ground is not the same as my ground. You might be in a 30-story building right now. I am like sitting on the first floor of the school. So, I mean, obviously, ground is a subjective thing, right? I mean, it depends on how you or where you're looking at it from. So potential energy is always measured relative, okay, relative to a reference point. That means you kind of need to tell people, or at least know from the question, where do they want height equals 0 to be. So this is the question of asking yourself, at what height are you assuming? So where is your height equal to 0? And you can pick that. You can pick that. So you can actually decide on yourself which area you want to be the height equal to 0. Because dropping, so another, I guess, very quick examples in here would be, it depends on, now let's say you have a table. So that's the table, right? So if you have an object here, same height, you have an object over there. So here's the ground. There's the table, right? Okay, so let's say you have something like that, right? So if I ask you, what is the amount of potential energy on the ball right now? It's not an easy question to answer, because you need to then ask me, are you dropping the ball on the table or are you dropping on the ground? Because they will have different amount of energy. You see? Even though they both start with the same height from the ground, but one can actually go to the ground, the other one will get stopped by the table. So the one that's stopped by the table, is not fair to use the ground as height equal to 0 then. Now, you will say, okay, so I can say the table is height equal to 0, then I can calculate the potential energy by doing that. So I can calculate the potential energy by setting the height equal to 0 here, and then doing your potential energy calculations. Now, you just have to tell people in the question that assuming height equal to 0 on the table. Like, you just have to literally say that. But on the other hand, if you're using the ground as height equal to 0, which is totally allowed, right? The ground as height equal to 0, then the potential energy value is going to be bigger. So even though same mass, same location in the air, but because you have a different reference point, obviously if you take the reference point of the ground, then the ground energy, is 0 potential energy on the ground and gets higher and higher. But if you're only dropping it to the table, then why not call the table equal to 0? Makes life easier. Okay, so you can say the potential. Now, which one is right? Both are. If you mention that you're measuring from the table, then both are right. If you don't mention anything, people are going to use what is the most conventional way or traditional way of thinking about things, which is ground equal to 0. So if you don't mention it, it means ground equal to 0. If you want to use somewhere else as a height equal to 0, you can. Just tell people what is that point. Okay, now very quickly, we're going through 2 examples and then this is done. Because what about this part? This part can only be done if you're physically in class, unfortunately. So we're only doing this 2 examples. Now, number 1. A 15 kilogram textbook is sitting on a 1.2 meter table. If the table is lifted 8.8 meters from the, so the book is lifted 0.8 meter above the table, how much potential energy does it have with respect to the table? And then part B, with respect to the 4. So what if you call the 4 equals 0? Now, so the first example is you have the book here, like right here, right now. Originally, it's like here. Okay, so you're lifting it on top of the table. So you are 0.8 meter this way, and the table is 1.2 meters like this. Okay, so if you're doing this with respect to the table, that means you're using the table as height equal to 0. Then, in that case, potential energy, which is mgh, is going to be mass of the textbook, 9.8 for gravitational acceleration, 0.8 from the table, 0.8 meter only from the table. And that gives you a potential energy as about 118 joules. Now, this is assuming that height equal to 0 is at the table. Okay, with respect to the 4 means set the ground equal to 0, which is perfectly acceptable. But then we will need the height, the total height of this, which is going to be 1.2 meter plus the 0.8 meter, so 2.0 meter. Okay, so if you do the potential energy equation again, it's going to be same mass, same acceleration, different height. And that will give you 294 joules. Okay, so who is right? Everyone is. Usually, if they ask you, hey, how much is the potential energy stored in the object in the book, in the textbook, right? You actually have to ask the questioner, from where? Right? Otherwise, I will say the answer is this one. Like if they don't say anything, if the question is really obvious that it's talking about like a platform, then of course, okay, use the platform, right? But when it's not clear, you mention it, right? You actually mention it. You say, oh, assuming ground is 0, then you do this, or assuming table is 0, and then you do that. Now, so another way, so this is like a spring version of it. Okay, like a spring version of it. An archer pulls on a bow string with an average force of 340 Newton. So this is like a bow, and the bow has like an elastic string attached to here. And the arrow, okay, the arrow is like here. And it has like a tail, like this, right? Okay, so when you pull onto it, so what happened is the elastic is going to bend backward. So you have your arrow now in here. Like that, ready to be fired. Okay, so how much do you actually pull it by? So, or like a nothing happened location will be the green line. So this is how much you actually stretch it by. Now it says in the question, this is 0.2 of a meter, and the applied force is 240 Newton. So that means there is a force pushing forward at 240 Newton. Just like when you, so because you pull it back, and there's a force pulling you back, pulling it back in, which is the spring force in this case, elastic force, spring force, doesn't really matter. So the work done to the bow is the applied force multiplied by the distance that it moves. Now, the applied force moves forward. The distance is kind of backward. No, actually, the other way around. I think the applied force, you're applying a force that's backward, but the arrow is shooting forward. But still, as long as they're parallel, we are okay. We are okay with that. And plus, especially, they're not asking you to do how much energy is lost by you. Is how much energy is gained by the arrow. Well, okay, that should be a positive number, right? Energy loss should be a negative number. This object will go faster and faster. So, I mean, not faster and faster, but it will accelerate before it hits the air and slow down. All right. So this is done. You should practice some of these energy on the worksheet, but if you look at the worksheet itself, okay, so in this equation that we have in here, mgh, right? The height has to be a vertical height. Okay, so this must be vertical. Now, on the worksheet today, you're going to see a height. Sometimes you're going to see questions where you have both a slanted height and a vertical height. Now, so what I'm talking about is, let me see if there's a way for me to get the worksheet. Let's see, is the worksheet bounded in here? If it is, then I can. Oh yeah, it is. So So let me kind of look at this one. So you look at number 3. So the box is at the top of a frictional incline. What is the potential energy with respect to the bottom right now? So that means set the ground equal to 0. With respect to the bottom means set the ground as height equal to 0. So now we say potential energy is mgh, right? So which one is h? The 7 or the 10? Okay, now remember, it's energy stored in gravity, and the distance is always measured directly up, which is vertical. So height in here means vertical height, not like something that is slanted. So it means this height. Okay, so that's the hint I will give you. And that's it. That's it. Like, it's really easy to do. Okay, now how about a pendulum? How about a pendulum? So if you look at question 4, that's a pendulum, right? Like the bob of pendulum. At the lowest point is 0.5 meters off the ground. At the highest point is 0.7 meters off the ground, 0.75 meters off the ground. What is the potential energy with respect to its equilibrium position? Equilibrium position means at rest, when it's sitting there nicely. This green line is the equilibrium or the at rest height of the pendulum, right? So if no one is paying any attention to it or pushing it, this is the location that it will stay in forever. So they said with respect to that, that means set height equal to 0 at that point. So that means your change in height for the mgh calculation is this little area. And it's easy to find, right? So again, that's all the hints I will give you. Okay. There we go. Now let me stop this first, and then this will be part 1 of the video. See, it's very short.